Hello, folks. Today we will be learning about collecting like terms and adding polynomials. This is going to be note 1.2 in our notes package. We're going to begin with going over a few definitions, then going through several examples to help us get how we can collect like terms and how we can add together polynomials. So first off, our list of definitions that we have, there's 6 of them here. Many of these work around this definition, which is a polynomial. So if we don't know what a polynomial is, it is a group of terms that are written together in an expression connected with additions and subtractions. So one example we could have for a polynomial is 2x plus 4. That is an expression that has two polynomials. It's known as a binomial. And because it's written with a 2x being one term, the positive 4 being another, and then they're connected with that plus that's happening. Another polynomial that we could have would be 2a minus 3b plus 5. So this is a polynomial that has 3 terms. You can see we have the 2a, the negative 3b, and the positive 5. This term that has 3 terms is known as a trinomial. And there are many other types. So we only really refer to the monomial, the binomial, and the trinomial with these names. Anything that has 4 or more terms we'll just probably refer to like a polynomial of so many terms. But the reason we focus on the monomial, the binomial, and the trinomial is they do come up quite a bit this year, next year, and the year after. So we tend to try to focus on these 3. So a monomial, just to go over real quick, is once again a polynomial that just has one term. That could be just 4x. That could be a term that's just a number, which is like 10. It could be a very complex one, which could be like negative 3x, y, z. So that last one is still only one term, even though it has 3 variable parts to it. Those parts are being multiplied together, so therefore that makes it a single term. A binomial, as we discussed, is that 2x plus 4 could be like x squared minus 3. Could be that negative 3xy plus 4ab. It could be anything, but it just can only be 2 terms. And then lastly, we have the trinomial, which we discussed was that 2a minus 3b plus 5. Another one could be x squared minus 2x plus 1. So in that case, the x squared and the negative 2x are 2 separate terms. The reason for that is that they have different variable parts, where the x squared has 2 x's being multiplied together, where the negative 2x only has 1x that's there multiplying. So we can write many more of these. Once again, we can have polynomials of, such a varying length. There's an infinite number of examples that we could provide, but we'll just focus on those 3, the monomial, binomial, trinomial. Degree. Well, degree is kind of a funny thing. We could sit there and go, is it the degree of a term? If I'm doing the degree of a term, then I'm just seeing how many variables are being multiplied in that term. So for an example, if I had that, we'll go with the monomial 4x. Sorry, I guess increase my marker size. This has a degree 1 because there is one variable being multiplied in it. I could have something that was, let's say that negative 3x, y, z. In this case, this is a degree 3 because there's 3 variables that are multiplying in that term. So anytime we want to find the degree of a term, we just have to figure out, how many variables are in that term. Like terms would be two terms that have that exact same variable part. So for an example, we could sit there and say, 4x and 3x. Those two terms have the same variable part, which is just x. Another one could be, minus 9, 5. Those are like terms. They don't have any variables in them, and we actually refer to those as constant terms. Another possibility could be something that's a little bit crazier, like that x, y, z. So we could have that negative 3 x, y, z, and then I could do a 7 x, y, z. So we see that it's the same variable part each time. That number out in front, which we refer to as the coefficient, the amount of that term that we currently have, it can change. It could be any number we'd like it to be, but the variable part just needs to be the same. So using these definitions, we're going to answer the following questions as best as we can. We'll look at degree in a couple different ways, so do take some time while we're going through the example to ensure how it is being asked of you. So if we look at our first problem here, negative 4x squared. In this case, I can see that I have that negative 4 that it's out front. That is our coefficient. Okay. Once again, I think I maybe have to quickly change these. Sorry for doing this in the middle of a video. Okay. So our coefficient is negative 4. The variable that's being used in this term, well, the variable is just x. So I do know that there's, two x's being multiplied there, but the variable that is there is just the x. If I wanted to refer to that variable part, it is x squared, but the variable that's in our term is just the x. The degree is referring to, how many variables do we have going on. So in this case, there are two x's that are, being multiplied for this term. So our degree is 2. Let's try to apply that to the second question. So in this one, we see we have a fraction of negative 2/3. I see I have a variable that's h, and I have a degree right now that is 7. So I have a coefficient that's negative 2/3. We have the variable that is h, and this time my degree is 7. For our third example, this one's a little trickier, and we usually see sometimes third, fourth examples, they do put little tricks in it for us. So I see I have my coefficient out front, my variable part. This time we have two types of variables that are going on. And then we have a different number of each variable in our term. So to go through this one, first off, our coefficient. I don't see a number here. So that's important. We have to come up with a convention that when we don't see a number for our coefficient, we're going to assume 1. The reason why we assume a 1 is because if I multiply by 1, it doesn't actually change the value of anything. So with that being said, whatever answers we get from knowing if A happened to be a number like 4 and B happened to be a number like 5, we could go and evaluate this term. and get an answer, and we would just have to make it negative at the very end or flip the sign. So in this case, if we're assuming that to be 1, then that would be a negative 1 out front. Our variables in this case is an a and a b. We have, 5 a's and we have 3 b's. So in total, we have a degree 8 term. There are 8 variables that are multiplying in this term. Next group of questions is we have a polynomial. So a polynomial, once again, could be any size, so that's why we're using that general term. We want to write them in descending order. So with that being said, that's based on degree of terms. So I'm going to write the largest degree first, and then second largest degree, and then continually keep writing them until we get to the smallest degree term. And then secondly, we're being asked to identify the degree of the polynomial. So that being said, that's different than a degree of our term. We're not going to sit there and add them all up. We're actually just going to state what is the term with the largest degree. Oh, if I could spell largest, I apologize. So those are the two things we need to do. So we have to go through and check out each of the terms, see if it's already written in descending order, like do we have to do any work at all? If not, we will rewrite it in descending order. And then we will just state the degree of the polynomial by stating the degree of that first term that we have once it's in descending order. Okay. So let's take a look at this first one. I have 3x to the power of 4 plus 5x to the power of 2 plus 3. So in this case, when I'm looking at these different terms, I can see that they're already written in descending order. Okay. I guess I'm zoomed in too much. I apologize. So because it's already in descending order, we look at that leading term, and that leading term tells us the degree of the polynomial. So in this case, that term has a degree 4, so the polynomial is degree 4. And sorry for the short form, I'm just not tons of space for me. Okay. When I look at the next question, I'm going through each of the different ones. I can see that it's not written in the descending order. I can see that negative 7x to the power of 5 is our largest degree, so I can already state the degree of our polynomial. It would be 5, but right now we don't have it written in that order. So I have negative 7x to the 5. The next one, I don't see any that have an x to the power of 4, so now I'm gone to the 5x to the power of 3. And I guess one thing we haven't discussed right now is there is no sign out front of that 5, that leading term that we have in that polynomial. Because there is no sign out in front, we're going to assume when I do not see a sign that it's positive. Now that is only for that term that's out in front of the polynomial, that leading term. If any other term, it should have a sign. So we can see in that the term, like we have a plus 2x squared, a plus 8x. We write that positive for the term everywhere else, but sometimes we just don't write it as a leading term. And we just got to remember that even though we don't see it, it is still there. Okay. The rest of it put together, we have plus 2x squared, plus 8x minus 4. So there we go. We have it now in descending order. Now that I have it in descending order, we're looking at this first term, and the polynomial is degree, if I can spell, polynomial. Sorry, sometimes I get ahead of myself in my head. Doesn't actually transfer to when I'm writing down. So our polynomial in this case is degree 5. Okay. Take a look at the last one. It's a third one again. As I said, usually third, fourth, we usually try to, throw something else in there. So in this case, we do have, our different terms. But our terms could have different variables in it. So I do have to ensure that if I'm trying to write the largest degree term first and write it in descending order, I have to account for all the variables that are in each term to come up with that answer. So in this case, I got 12ab minus 9a squared b minus 5 plus 8a. So in this case, that negative 9a squared b is the largest degree term because there are 3 variables multiplying in that term. There are 2 a's and 1 b. The next one is the 12ab. Once again, I put that positive there because I have to assume out front, if there's no sign, that it's a positive term. Then I'm going to write 8a because it has 1 degree. And then the last one that has 0 degree is that minus 5. Look at our first term. That first term tells us that the degree of the polynomial is 3. Is degree 3. Okay. So this idea of writing our polynomials in descending order, it's something that you're going to use, moving forward. I'd recommend if you ever get a polynomial, if it's not descending order, to rewrite it in that way. And it's going to help you with many skills and concepts that we learned and this year, next year, and the years to come. Okay, our next questions are called collecting like terms. So collecting like terms are when I have 2 terms that have the same variable part. If we're collecting like terms, we're really just trying to simplify the expression into, a smaller number of terms where we put like terms together by adding or subtracting their coefficients. For this first example, we have, 8n minus 4. I like thinking of these like, if it's too difficult to refer to the n as like something that we're adding or subtracting, you could try to make it more of a physical concept. Like I think of apples. If I had, 8n minus 4n is like 8 apples, and I take 4 apples away, how many apples do you have left? So in this case, I have 8 n's, and I'm taking 4 n's away, and that leaves us with 4 n's left over. And the reason we could do that is just because, they're the same term. And the next question, we have that idea. We still have those same terms, but it looks like we have 2 different types of terms inside our polynomial. So I can only put together like terms. Like if I was trying to do that first example and I said I had 8 apples and I took away 4 bananas, it doesn't make sense that I can actually do anything with those. So in this case, we'll look at each like term separately. So I have 5 x's, and I'm adding 12 more x's. So that gives us 17 x's in total. I look at my other type of term, my constant terms. I have negative 8 minus 9. That gives us minus 17. At this point, I can't put those terms together anymore. They are not like terms. They are unlike terms. And therefore, unless I know the value of x, I can't go any further. Now, if, and this is I'm speculating here, if we happen to find out x. So let's say if, x equals 3, then we could finish off and find the answer for our expression. Anytime I substitute in, please always substitute in, with brackets. So that's 17 times 3 minus 17. That's me taking our expression that we had here and rewriting it with the 3 in the appropriate spot. I can go and evaluate. So 17 times 3, if you're not quickly doing that in their head, that's 10 times 3, which is 30, plus 7 times 3, which is 21. So we get 51 minus 17. And that leaves us with 34 being our answer. So that's if, we know what x is, we could continue to evaluate and get it down to a single number. But when we don't know what x is, we do have to leave it as that 17x minus 17. Okay. Next one, similar idea. I do have my, 24 and 2.8. I have my b minus 11b, so I could quickly write this. Once again, I'm going to choose the order that's going to help me out. I do want to have that descending order. I want to have that leading term to be the largest degree. So in that case, I'm going to deal with the b's first. I have 1b, and I'm taking 11 away. So that gives me negative 10 b's. Then I'm going to go deal with my constant terms. I have 24 plus 2.8. So that gives us 26.8. Sorry for the bell. So that's us collecting like terms. Okay, us adding polynomials on the next page. It's going to follow this exact same process as us collecting like terms. So I'm going to skip over our finding sum of polynomials real quick and just jump into our examples that we have. I'm going to do these 4, and I'm going to leave the bottom ones for us to do maybe in class or another time. So looking at our examples here, when I'm adding polynomials, exact same thing. I'm looking to see which terms are like, and I'm just going to add together those like terms. So I have descending order. I'm going to do my y to the power of 2's first. I have 8 of them, and then I'm adding 3 more. So that gives us 11 y squares. I then have positive 2y plus 7 more y, so that gives us 9y. Those 2 terms that we have remaining are unlike terms because we have a different number of y's being multiplied in each one. Next example, same thing. I have my 3, or x cubes, or x to the power 3. I got my x to the power 2's, x's, and my constants. So right now, we see that they're both written in descending order. This is what would help us out. I'm not trying to figure out, what the new order is going to be, trying to determine what the highest degree term is going to be. They're written in that order so that I can easily work from there. So I have 3x to the power 3 plus 7x to the power 3, so that gives us 10 x's to the power 3. I have minus 4x to the power 2 plus a negative 9x to the power 2. So those are both, I'm adding 2 negatives. So that gives me negative 13x squared. I have a positive 4x plus a positive 2x. So that gives me a positive 6x. And then I have a negative 2 plus a positive 4, which gives us positive 2. Okay. For this one that we have for question 3, it starts to stump us a little bit. We can see that I have r to the power of 4. I don't have any more of them. I have an r to the power 3 here. I have an r to the power of 2 there. I have an r to the power of 1. And then I have 2 constant terms. So until I get to those constant terms, I have unlike terms in this entire polynomial addition. Well, that just means I have nothing to add to the terms that I already have. So I would just rewrite the ones that don't have any like terms. And I'm going to do so in that descending order. So all of these terms so far have no like terms to combine with until I get to that positive 3 plus 7, and we're left with 10. So if I have no like terms to put together, the term that I have just stays how it is. Last one, we have a whole bunch of stuff going on. So just take your time, try to pick out the largest degree term. I hope they're written in order. That usually helps out. So I see I have a y to the power of 3. I have 2y squareds over here, or y to the power 2. I have a negative 9y, a plus 8y, and a minus 3y. And then I have a positive 2 and a minus 12. So once again, write them in descending order. So I have 12y to the power of 3. My y squareds, I have 6y squareds plus 2 more, so that's 8y squared. So even though that's within the same polynomial, I'm just collecting those like terms. I have negative 9y plus 8y, so that brings me up to a negative 1y just in that first polynomial. And then I'm adding a negative 3y, so that's going to give me a negative 4y total. And then I have my constants, which are the positive 2 minus 12, which is negative 10. Okay. So that's how we add together our polynomials. You can see that I'm using highlighters to help me out. I would recommend something like that. Or if you're underlining, if I didn't have highlighters, then I would use something like, if I didn't have highlighters, I might quickly number like terms like that so I know which ones go together. Okay. The ones down here, very similar. You're going to add up, but we're applying it to perimeter. I can try doing these real quick. So I have the perimeter of a square, which is 4 times that side length, which in this case is 4 times 5x. And if I have 4 5x's, then that's 20 x's total for our perimeter. For this, it looks like a trapezoid's perimeter. I'm going to assume that the top and bottom are parallel. Our perimeter is once again just adding around the outside. Anytime I'm subbing in, always sub in with brackets. I'm just going right around the outside, adding together each of the sides. So we'll underline our largest degree term first. Looks like those are the c squareds, or c to the power 2. I then have my c terms, and then I have my constant terms. Constant terms. So putting together my leading term first, I have 9c to the power 2 plus 8c to the power 2, so that gives us 17c to the power 2. I have minus 3c plus 17c plus 2c, so that gives us 16c. And then I have a minus 4 plus 3, so that gives us a negative 1. So our perimeter expression for the trapezoid is 17c to the power 2 plus 16c minus 1. I have no clue what the actual perimeter is until I know what the value of c is. That is how we add polynomials and collect like terms. If you guys have any questions, please feel free to bring them to class.